Welcome to our presentation today. Our topic is analysis of environmental impact of e-scooter sharing services considering product reliability characteristics and durability. My name is Semih Severengiz and I'm from the Laboratory for Sustainable Technologies of the Bochum University of Applied Sciences. My co-authors are Nora Schelte from the same affiliation and Professor Stefan Bracke, Chair of Reliability Engineering and Risk Analytics at the University of Wuppertal. Our agenda of today is about the challenges of urban mobility and about the advantages and disadvantages of more reliable electric scooters from the perspective of ecological sustainability. Next is the methodology and finalizing with a conclusion. Greenhouse gas emissions are one of the major challenges caused by transport. This slide shows the greenhouse gas emissions of the European Union. As you can see on the left, the transport sector is responsible for 1/3 of all emissions. Nearly 3/4 of transport emissions are caused by road transport. Passenger cars have a share of 60% of road transport emissions. Therefore, it is quite important to find alternative mobility solutions for individual transport with cars. One possibility to foster new mobility systems are e-scooter sharing services. E-scooters are touted as an ecologically advantageous mode of transport by sharing providers, as they could be a solution for the last mile of public transport and do not have direct tailpipe emissions. However, e-scooter sharing has potential disadvantages like the collection of e-scooters and batteries by service vans. Moreover, previous studies on e-scooter sharing have shown that the environmental impact is significantly affected by their short lifetime. You can see examples of scooter modes with different lifetimes. On the left side, you can see older scooter models. These models are lighter and have fewer aluminium components, which reduces the environmental impact of the production phase. However, these scooters are also less robust and have a shorter lifetime. The newer scooter models with swappable batteries are heavier, but also more robust and durable. However, this also increases the environmental impact of the production phase. In our study, we analyzed what are the advantages and disadvantages of a reliable e-scooter from the perspective of ecological sustainability. Therefore, we developed a concept to include reliability characteristics into the methodology lifecycle assessment. Firstly, we developed reliability modes regarding the failure behavior of main scooter components based on a synthetic data set. Secondly, we conducted a lifecycle assessment for e-scooter sharing and afterwards analyzed different case studies in the field of innovation cycles and product reliability, the influence of component durability on scooter lifetime and energy demand in production, and maintenance strategies. Let's talk about our methodology of the reliability model. The equation left down shows the underlying viable distribution model for the printed reliability analytics. The graphic shows the schematic failure rate lambda of technical complex products. 3 failure phases are visible. Early failure phase, so-called childhood illness, random phase, and wear-out phase. Within the presented study, we are concentrating on wear-out failure modes with respect to important e-scooter components. This slide shows an overview with regard to the expected lifespans of main e-scooter components from the reliability engineering point of view. The overview with respect to failure behavior of important e-scooter components using viable models is our next slide. The x-axis shows the kilometrage, the y-axis shows the failure probability in case of an upcoming failure symptom. I will provide an example. The e-scooter battery has a kilometrage 10,000 kilometers, a failure probability of 48%. These reliability models are important for calculating expected failure probabilities within the usage time. It allows the calculation of spare parts, maintenance intervals, etc., which have a clear impact on lifecycle assessment. Lifecycle assessment is an instrument for quantifying the environmental impact of technical systems or services throughout their entire lifecycle. The goal of this study is to examine the lifecycle global warming potential, or called GVP, of e-scooter sharing in consideration of reliability characteristics. The functional unit is 1 passenger kilometer. And now results. In this slide, you can see an overview of the results of our life cycle assessment. Using the basic assumptions, the GVP of the model 2020 is 130 grams CO2 equivalent per passenger kilometer. Different scenarios, including reliability aspects, results in a range between 116 and 164. In order to assess the impacts of product reliability on the life cycle assessment of e-scooters, we examine 3 case studies as examples, which I will explain in the next slide. Case study 1 shows the impact of innovation cycles and upgrade capability on life cycle assessment results using the battery as an example. The average scooter lifetime is 4,200 kilometers. As you can see, the battery lifetime is longer than the scooter, which have several effects on innovation cycles. On this slide, you can see our assumption for the 4 cases we analyzed. Currently, scooter models are available with replaceable and fixed batteries. A possible advantage of replaceable batteries is that the battery is upgrade capable. This means it could be replaced by a successor generation of batteries with better range. Since the innovation cycles of scooters and batteries are not synchronous, it may therefore be possible and reasonable to replace the batteries of a scooter sharing fleet even within the short life of the scooter. On the other hand, the battery could be removed from the scooter after the end of the scooter's lifetime and be used in a second life application. In the scenario base case, the battery is not replaceable. Also, the battery has a lifetime kilometerage of more than 4,200 kilometers. It cannot be used beyond the scooter's lifetime. For the scenario second life for batteries, we assume the battery is replaceable. We assume it is used throughout its entire lifetime beyond the scooter's lifetime, for example in other scooters or new applications like charging stations. In the scenario 1.3, battery upgrade, we assume that the replaceable battery will be upgraded by an improved battery after 6 months. Due to innovation cycle, the upgraded battery has an improved range of 45 kilometers. It is assumed the batteries are not used in second life application after the upgrade or beyond scooter's lifetime. In scenario 1.4, the battery is upgraded after 6 months as well. However, the battery will be used in second life use case for their full lifetime. Here you can see the results of case study 1. It is divided into the production of scooter and battery, transport, electricity demand, and the use phase, logistics, and end of life. You can see that the majority of GVP is caused by production. The results for case study 1 demonstrate that a battery upgrade could improve electricity demand and logistics in the use phase by 20%. If the battery is upgraded and used in second life, the total GVP decreases by 11% to 116 grams CO2 equivalent per passenger kilometer. And now case study 2. Case study 2 analyzes the influence of component durability on scooter lifetime and energy demand in production. As explained before, the lifetime of e-scooter ranges between 6 and 12 months. Compared to the model 2020, the model 2018 has shorter lifetime of 2,100 kilometers. The battery of this model has a range of 22 kilometers. Below, you can see how we calculated GVP for different lifetimes. And now coming to one of our main findings. This graph shows the GVP of both models for different lifetimes. The break-even point P is reached when the GVP model 2020 equals the GVP of the model 2018 for its maximum lifetime. Assuming the maximum lifetime of the model 2018 is 2,100 kilometers, the break-even point of the model 2020 is accordingly at the lifetime of 3,325 kilometers. And finally, case study 3 compares the impact of different maintenance strategies on lifecycle assessment results. The charger and handle are considered in details as parts that are likely to fail and need to be replaced during the lifetime of the scooter. The calculation of the GWP is based on the assumption that the total kilometerage in scooter is reduced by downtimes. It is assumed that the downtime is 30 days if a component fails unplanned and 1 day if it is maintenance preventive. In case study 3, we analyzed 3 different maintenance strategies. In the scenario firefighting strategy, we assume every component which fails will be replaced unplanned. Therefore, the rate of replacement of a component equals the failure probability of a component. The probability of the components charger and handle to fail within the scooter lifetime is 57% for the charger and 13% for the handle. In scenario periodically scheduled, we assume every scooter will be maintained at 1,400 and 3,400 km. We assume that because the failure rate of the charger is 5% at 1,400 km and of the handle at 3,400 km. Therefore, only for 5% of the scooter fleet the components need to be replaced unplanned, with a downtime of 30 days. The rest will be replaced preventive with a downtime of 1 day. However, it is assumed that all components are replaced preventive during maintenance, even if they would last longer. In scenario predictive maintenance, we assume components that are replaced predictively with a downtime of 1 day. It is assumed that due to the predictive maintenance, only slightly more parts are replaced than would be actually have failed. Due to the lower downtime, the GWP of scooter production based on passenger kilometers decreases in scenario 3.2 and 3.3. However, this advantage is outweighed by the high spare parts demand in scenario 3.2. Overall, according to these assumptions and calculations, it is possible to decrease the GWP by 4% compared to scenario 3.1 by using predictive maintenance. And finally, now our conclusion. We have discussed different examples how to consider reliability characteristics into lifecycle assessment and lifecycle engineering. We used the example of the battery to outline the contrast between lifetime, product innovation, and environmental impact. It shows that modular, replaceable components have the potential to reduce the GWP significantly, in this case by 11%. However, the importance of using replaced components in second life application was highlighted. We have demonstrated a high optimization potential in lifecycle engineering of e-scooters by increasing the durability of components without simultaneously increasing the GWP of production. With regard to flexible mass customization, we have shown it may make sense not to improve the durability of components at all costs. For example, e-scooters in private use are treated more carefully, maintained more often, and are less affected by vandalism. We presented approaches how to include maintenance strategies into lifecycle assessment. It is shown that predictive maintenance can reduce the environmental impact by 4%. Overall, the study was able to indicate a correlation between reliability characteristics and the environmental impact of e-scooter sharing. However, product reliability should be further investigated in future studies based on real data. Furthermore, it is recommended to analyze the impact on other ecological as well as economic and social aspects. Thank you very much for your attention.